So today we're going to look at how roots interact with the other numbers and processes we have in math, how they interact with addition, subtraction, multiplication, division, but mainly how to simplify them. So that way if we have a big root, we can kind of piece it down to a smaller, more manageable number that we can hopefully work with a little bit more rather than just some big giant root we can't do anything with. So just to make the comparison here, what we're doing is simply what we do with fractions, just with roots. So with a fraction like 16/20ths, we say that's a pretty big fraction. I can reduce that because both 16 and 20 can be divided by 4. So I divide the top by 4, I divide the bottom by 4, and I get 4/5, which is the exact same fraction, the exact same amount. It's just smaller numbers, easier to manage. That's what we do with roots. The problem is that we can't treat roots just like fractions because they're just a single number rather than two numbers divided together. So with roots, the way we simplify is we use what are called perfect squares. So if you remember, perfect squares are numbers that when you square root them, you get a nice whole number back. So for example, 9 would be a perfect square. So if I take the square root of 9, that's going to give me a nice whole number of 3. So 9 is a perfect square because it gives me a nice whole square root. 7 would not be a perfect square because if I take the square root of 7, I get a decimal. And you can use a calculator to type that in if you don't believe me. So we use these values of perfect squares, square roots that give me a nice whole value, to help reduce down the size of bigger roots. So for example, 40. The square root of 40 is a rather large number. Well, maybe not necessarily large, but it's a rather large decimal, we'll say. It has a decimal point, and so a bunch of numbers behind it, and we don't really want to bother with it. But I don't have to leave it as square root of 40. I can actually reduce it down a little bit so that it's still the same amount, just looks a little bit smaller. So I'm going to ask myself, how can I split 40 up? What's a perfect square that goes into 40? What's a perfect square that can be divided into 40? Well, 4 is one. 4 is a perfect square. So I can change 40 into 4 times 10. And the reason I do this is because with square roots, you can apply it individually to multiplication, unlike you can with addition or subtraction. So when I split 40 into 40 times 10, when I simply write it out a different way like I'm doing here, all I have to do now is think, well, right here, the square root of 4, I know what that is. The square root of 4 is just going to be 2. Now the square root of 10, this piece, that I can't do. I don't know what the square root of 10 is. There's no easy way to do that. So I'm just going to leave it as root 10. So this is the simplified or the reduced form of my starting value, root 40. The exact same number, the exact same amount of stuff, it's just written with a smaller value and with a whole number part to it that we can then work with in some cases. So the goal of reducing a root is to figure out what are the perfect squares that go into it, and then to take those out, simplify those, and then leave the part you can't do inside the root. That way you basically do as much of it as you can, and then the part you can't do, you just kind of leave off still there. So this says 2 times root 10, but kind of like with variables, we don't write the times symbol, we just say 2 root 10. We don't say 2 times, we just say 2 root 10. It's implied that's multiplication. So for the next ones here, square root of 180, again, I'm thinking what perfect squares go into 180? Well, I know that 9 does, so I can split this into the square root of 9 and 20. And then 20 has a 4 in it. I can take a 4 out of 20, so I can split this even further. I can go square root of 9 times 4 times 5, because this is 20, and altogether it's 180, so it's the same value there. And I think I've gotten about as many perfect squares as I can. 4 and 9 are both perfect squares. 5 doesn't really have a perfect square that goes into it except for 1, which wouldn't change much. So what I'm going to do is I'm going to say that this right here, that's 3. This right here, that's 2. So 3 times 2 times this right here, well, that's just root 5. I don't know what that is, so I'm going to leave it as root 5. I know what 3 times 2 is, though. 3 times 2 is 6, so this would be 6 root 5. That's all it is. If we go to the next one here, root 75. Okay, I'm thinking here, root 75. 75, well, 25 and 3, that works. So 25 times 3. 3 I can't do, that's going to be square root of 3. But the square root of 25, well, that's just 5. So that'd be my simplified form there. And the last one, 90, well, that's going to be 9 and 10. We already did 9 before. So this right here, that's just going to be a 3. And this right here, well, that's just going to be root 10. So I'm looking for those perfect squares that go into the values that I can then take out and root simply. Because looking at 3 root 10 means a little bit easier to do than do root 90. And there's another reason why we simplify them like this is because now that we have a whole number part, we can actually start combining stuff we couldn't necessarily combine before. Because now that we have it reduced, we can start to see that how certain roots match together. So for example, if I have 2 roots and I want to put them together, I can as long as the roots are the same. It's kind of like variables. An x plus an x is a 2x, whereas an x plus a y is just going to be x plus y. Roots follow that same pattern. 3 root 2 plus 4 root 5, well, this is just done. I can't do anything more there. I can't put a 3 root 2 and a 4 root 5 together because root 2 and root 5 are different. I really don't know what they are put together because I can't just say it's root 7 because it doesn't work like that. I can't just say root 2 plus root 5 is root 7 because addition doesn't have that equality property that multiplication and division do. But on the other one, 3 root 2 plus 4 root 2, well, that I can do. Because it's like saying 3 root 2's plus 4 root 2's together is just going to give me 7 root 2's. Kind of like 3x plus 4x is 7x. Well, 3 root 2's plus 4 root 2's will give me 7 root 2's. So as long as the root parts are equal, as long as the root portions are equivalent, then we can add them together. But if they're not, then we have to keep them separate, just like we do variables. So let's try this one here. So we're just going to kind of look through the problem like we did with variables and see where are the roots that are the same that I can put together. Any roots that aren't the same, I'm going to leave out. So here, 3 root 6 minus 7 root 6. So 3 minus 7 is negative 4 root 6. Plus, this doesn't have anything to combine with, so it's going to go straight down here. 8 root 5, and I'm done. Okay? There's no more to combine there because root 6 and root 5 are different, so I'm just going to leave them separate. So again, combine what you can, leave out what you can't. And in the next one, it looks at the first glance like we can't do anything. Okay? We can't do 2 root 5 plus root 20 because root 20 isn't the same as root 5. But that's why we learned how to simplify them, because this root 20, if I recall, that's like saying 4 times 5. And I can do root 4. Root 4 is just 2. Then bring down my root 5. So now I have this, 2 root 5 plus 2 root 5. Well, now my roots are the same. So now I can put them together and say that this is just big 4 root 5. 2 plus 2 is 4. Keep the root just like you would keep a variable. So that's one of the reasons why we simplify roots, is so that when we have a problem like this, we don't just say, okay, well, I'm done here, I can't do anything. Well, if you work a little bit and simplify the roots, you can actually get it down to a single value rather than an addition problem, which allows you to work even further for more complex issues. So that's one of the reasons why simplifying roots is important and powerful, is because it allows us to take a problem that we think can't be done, but after we manipulate a little bit, we figure out that it can actually be done. And then just to finish it off here, if we put into more familiar looking problems, again, the first one there, another reason why we simplify roots is it allows us to get rid of division sometimes. So in this case here, 12 minus root 18, well, that can't be done. But root 18 can be simplified a little bit, because root 18 is like root 9 times 2. And I know what root 9 is. Root 9 is 3. So if I write this again, it's like 12 minus 3 root 2 over 3. Well, I know what 12 divided by 3 is. This right here, 12 over 3, that's 4, minus 3 over 3, well, that's 1, root 2. Because again, this last term, that 3 root 2, that's one chunk. So when I divide that by 3, all I need to do is cancel out the 3, and I just keep the root 2. Now, another way of writing this would be simply 4 minus root 2. You don't have to write down the 1. It's kind of like writing 1x versus x. Yes, you can, but you don't have to. And the other one's kind of the same way. Right now, these roots don't look like they have anything in common, but if I look a little bit, 63, well, that's root 9 times 7. 28, well, that's root 4 times 7. So if I play around with this a little bit, this is going to give me 3 root 7 minus 2 root 7 all over 2. Well, 3 root 7 minus 2 root 7, that I can do because they're both root 7s. So 3 minus 2 is going to give me negative 1 root 7 over 2. And some people will leave their answer like that, which is fine. Other people will write it like this. They'll say negative 1 over 2 root 7. Again, treating the 7 as like a variable, like negative 1/2 x, negative 1/2 root 7. And that's another way you could write it. That's a perfectly legitimate way of writing it. So either of these, this one or this one, would be okay. They're both correct statements, just different ways of writing it. So again, the reason we simplify roots is to make problems that were seemingly impossible to do a little bit more possible and a little bit more manageable. Hope you enjoyed the video. Have a good day.